Hi everyone, welcome to Integral Calculus. Today we explore lesson 8.3, hydrostatic pressure and force. Number one, the idea. Suppose a thin horizontal plate of area A is submerged in a fluid of density ρ at a depth of d meters below the surface of the fluid, as seen in the picture on the left side. The fluid directly above the plate has volume. That would be area times the depth, so AD. Mass is density times volume. Which is rho AD. Force, which is mass multiplied to the gravitational acceleration. Mass is rho AD. The gravitational acceleration is G. Very cool formula. We define the pressure on the plate to be force per unit area. So pressure on plate is force over area. Or P equal F over A. We know the force is mass times acceleration, rho AdG over A. And this simplified to be rho dG. Very nice formula for the pressure. If you take closely at the force equation, force is just pressure multiplied to area of the plate. So rewrite this as the rho dG times A, which is pressure multiplied to area. Very nice. We're going to be using another fact. And that is the pressure is the same in all the direction. At any point on the plate. For instance, a diver feels the same pressure on nose and all ears. What this means is that the pressure in any direction at a depth d in a fluid with density rho is given by pressure is rho dG. If we are using mass density, and the pressure would be delta times d if we are using weight density. Mass density is the kilogram per cubic meter. Weight density is pound per cubic feet. Let's take a look at how we apply the hydrostatic pressure and force. Number two, applications. Example. Find the force on the dam due to hydrostatic pressure. A, if the dam is full. B, if the dam is half full. This is the dam right here. And let's take a look at the case in which it is full. So in A, the dam is full. So that means water is filled all the way up. That is a trapezoid-shaped dam with the two parallel sides, one at 40 meters, the other one is at 20 meters, and at a height of 30 meters. So in order to calculate the force on the dam, notice that the pressure varies with depth. So we got to figure out the force on a sample strip. Let me sketch a sample strip here. Force on sample strip. We know force is pressure multiplied to area up strip. The pressure is, well, the formula is rho G multiplied to the depth D, the area's length and width. Okay. Next step is, well, we can use the y-axis to make life a little easy. So I'm going to use this as the y-axis. I'm going to cut right in the middle. It's the y-axis. Down here is 0. And then up there is 30. The distance here is y. So that means the depth of the strip is 30 minus y. Rho G 30 minus y. The length would be the green part right here. That would be the length of the strip. So we can figure it out. I'm gonna draw this out right here. Place the y-axis so that's right in the middle. So this would be 10 and the other side would also be 10. So this small side right here, it will be x. And then we know that this small height right here would be y. Ah, there's two right triangles, the smaller one and the bigger one. We can figure out x using the right triangle, similar triangle. X over y equal. This distance right here is half 40 minus 20. So this would be 10. And then the height is 30. So it's 10 over 30. Which tells us that x equal to 1 over 3 y. The length is 2 times 10 plus x. And the width is the small change in y. We know what x equal to do the substitution. rho g 30 minus y multiply to 2 times 10 plus 1 over 3 y dy. Rho g 30 minus y, we can factor out 1 over 3. So let's get 2 over 3, and this would be 30 plus y dy. 2 over 3, rho g 900 minus y square dy. Amazing, huh? Since this is the force of a submerged strike, in order to figure out the force on the dam, we got to sum up all of the submerged strike, and the sum in is the integration. Force is integration from the bottom to the top of the dam, because the dam is full. 0 to 30. In here is 2 over 3 rho g 900 minus y square dy, which is 2 over 3 rho g 900y minus y3 over 3. Evaluate from 0 to 30. And this gives us 2 over 3 rho g. You do the substitution, then you will get 900 times 30 minus 30 to the power 3 over 3. Yeah. Simplify that with a fraction, and we get 12,000 rho g Newton. Well, if we know the density of water, then we can do the substitution. The gravitational acceleration is 9.8, so you can easily compute the actual force. Now let's take a look at B. Yeah, what happened if it is half full? So in case it is half full, then this is what half full look like. Okay. So same thing here. We're gonna get a sample stripe. This would be a strip. And then the force on this sample strip would be pressure multiplied to area of strip. The pressure here is rho g d. The area is length and width. We know the length is the same, the width is the same, so that would be 2 times 10 plus x dy. Rho g, the depth here is different. So if we draw the y-axis that go right in the middle, right? So this is 0, and then the number right here at the top of the depth is 15, because it is half full. So if there is y, then this 15 minus y. The depth is 15 minus y. And the area would be the same. 2/3 times 30 plus y dy. So this would give us the 2/3 rho g. Multiply them together. We have minus y squared minus 15y plus 450 dy. So the force would be the integral from 0 to 15 of 2/3 rho g minus y squared minus 15y plus 450 dy. And if you work out the integral, then you will get 2.625 rho g Newton. The force is way less than when it is full. Okay, there's another cool application. Let's take a look at it. Second application, a cube is sitting on the bottom of a pond having water level 1 meter deep. Each side of the cube is 20 centimeters long. We want to find the hydrostatic force on the top of the cube and the hydrostatic force on the side of the cube. Yeah. Let's just sketch out. So right here's the water, right, on the pond. And it is 1 meter deep. So down here we have a cube. Cube is only 20 centimeters or 0. The hydrostatic force on the top of the cube is gonna be, well, there's only one part of the cube that is right on the top. It's right here. This is just a thin horizontal plate. So we can do A right away. Force is pressure multiply to, well, area of the plate. The top is just a plate. Pressure is rho d g. Rho gd is better. The area of the plate, right? So it's the 0.2 square. We can figure out the depth here. We know that the cube is 0.20 centimeter long. So the depth is 1 meter minus 0.20. Rho g 1 minus 0.2 and multiply to this 0.04. Since the number is small, I'm going to do the substitution here. We know water has a density of 1,000 kilogram per cubic meter. The gravitational acceleration is 9.8. And this one is 0.8, 0.04. Multiply them together, we have 313.6 Newton. In B, we're going to find the hydrostatic force on the side of the cube. Notice that the pressure varies on the side because on the side, the depth is different. I'm going to do a sample. So on the side, right, there's the sample strip. The force on this strip would be pressure multiplied to the area of the strip. The pressure is rho g d. The area is length times width. Okay, rho g. If you look at the depth here, we can use the y-axis, and if we use the trick with the y-axis, then the distance from here to the bottom is y. So that means the distance from the top to the stripe would be 1 meter. So 1 minus y. 1 minus y. The length here. Well, that is the length on the side of the cube is 0.2 meter. The width is, well, a small change in y, dy. And this gives us the 0.2 rho g 1 minus y dy. So that means we can do B. The force on the side would be the force on each strip, and we're going to add them up. So to add them up, we use integration. Force would be integral from, well, if you look at the stripe here, they vary from the bottom of the cube to the top of the cube. So 0 to 0.2 meter. 0.2 rho g 1 minus y dy. 0.2 rho g y minus y squared over 2. Evaluate from 0 to 0.2. And this would be 0.2. Rho is 1,000. G is 9.8. 0.2 minus 0.2 squared over 2. This gives us 352.8 Newton. And ta-da! We are done. Thank you for watching. I hope you found the content useful. Please like and subscribe to help the channel grow. I will see you in the next video.